Hello, good evening. Can you hear me? Hello. Hello, can you hear me? Okay, cool. We will get started in a couple of minutes from 6 o'clock. Fine. Okay, yeah, we'll get started for today. So, yeah, good evening, everyone. So, this is Diljit Datta. So, we'll be looking through session 6 of this course, that is optimization methods. Today, we'll be covering the problems and concepts that has been taught in the week 6, that is constraint optimization with inequality constraints. So first we'll look into the standard form of like how does a problem with optimization problem in inequality constraints look like. So this is the standard form of this optimization problem with inequality constraint. So we have to minimize the function f of x. So it will be subject to a constraint where gj of x is less than equal to 0. Since it is less than equal to 0, inequality constant and this less than equal to 0, so we can add a slack variable yj square to make it a equality constant. We're taking yj square because even if yj is negative, the yj square will be positive. So summation with gjx it will be equal to 0. So this whole term gjx plus yj square we can will note it. I will write it substitute in the form of capital G of xy is equal to 0, where capital Y is equal to y1 to ym and j goes from 1 to m. M is the number of constants. So now we have now we have the problem in the similar formulation that we saw last week. That is, we have a minimization function and a equality constant. So we can use the Lagrange multiplier that method, Lagrange multiplier method to get the optimal solution. So we'll write the Lagrange function for this problem. That is L, X, Y, and lambda. Lambda is the Lagrange multiplier. So it will be f of x plus g equal to 1 to m lambda j into gj of x, y. Remember, this g is the capital G, that is the whole function. This one. So the now we'll have to, as per what we have seen last week, that we have to take the derivative with respect to all the variables. So what are the variables here? Variables are xi, lambda I and yi. So lambda, sorry, xi, lambda j and yj. Xi is the number of variables, that is I goes from 1 to n. Lambda j and yj are depends on the number of constants. So j goes from 1 to m. So with there m constant, there will be m lambda j's and m yj's. So we'll have to take the differentiation, first derivative with respect to each of these variable. So first we will see with the derivative of the Lagrange function with respect to xi. So del L by del xi equal to del f by del xi plus sigma j equals to 1 time lambda j del of gjx by del of xi is equal to 0. This is the first condition. The second one will be, we will take the differentiation with respect to lambda j. So del L by del lambda j. So we'll get the first term, differential first term with respect to lambda will be 0. So we'll get only the second term. So second term, del lambda j by del lambda j is 1. So the remaining term is gj of xy. So which is equal to small gj of x plus yj squared. So this is equal to 0. This is the second condition. And the third necessary condition is that del L by del yj is equals to 0. And if you take the differentiation with respect to yj, so the first term, differential first term with respect to yj will be 0. Then in second term, we can take lambda j out of the derivative, and capital G we can write as small g of x plus yj square. So differentiation of small g of x with respect to yj is 0. The remaining term is del yj square by del yj. So the whole term will come as 2 into lambda j yj is equals to 0. So these are the three necessary conditions that are required for solving this problem. Now let us look at look into the third condition. The third condition says that lambda j yj is equal to 0. Now there might be two conditions here. One is where lambda j is equals to 0 or yj is equals to 0. So let us see in the first condition what will happen if lambda j is equals to 0. If lambda j is equals to 0, it means what? That constant is not an active constant. That constant we can neglect. If lambda j is equals to 0, that means that constant doesn't have a significance. So in that case, we call that constant a inactive constraint. And the second condition is yj is equals to 0. When yj is equals to 0, this will give us the function gj of x is equals to 0. And this comes from where? This comes from the second one. Comes from the second equation. It is capital G of x equal to 0. If yj is equal to 0, so then only gj of x is equals to 0. So now this becomes the active constraint. So we'll denote the J1 as a set of active constraints and J2 as the set of inactive constraints. Since there might be, we told that there might be from J goes from 1 to n. Out of n, J1 are active constraints and J2 are inactive constraints. So we can now modify our optimality problem as that the first equation will be same, that is del f by del xi plus sigma of j equals to 1 to j1. So this will only this is only for the active constant. J is only for the active constant, is j1. Lambda j into del j of x by del xi is equals to 0. Second condition is gj of x is equals to 0. It is j belongs only to j1. It is only for the active constraints. And thirdly, gj of x plus yj square is equal to 0. This is for the inactive constraints. Okay. Now what we can do, we can write this equation in this form. We take the lambda j, we take the del f by del x part into the right hand side. So if we take it into right hand side, we will get the equation in this form, that is minus of del f by del xi is equals to lambda 1 del g1 by del x1 plus lambda 2 del g2 by del xi and up to lambda p into del gp by del xi. So here P is the number of active constants. P is the number of active constants we are considering here. So we can write this equation in this form: minus of delta F is equals to lambda 1 del G1 plus lambda 2 del G2 and up to lambda P of del GP. So we can write this. Now let us take only two constants. Generally, what happens, we are considering only the planar function, like we are solving a optimization problem in a plane. That is plane. There is only two variables. In that case, we will have two constants. And if we take only two constants, so it will be minus of delta F equal lambda 1 del G1 plus lambda 2 into del G2. So I think the sir has taught in the class that if this is the planar, it is a solution, that is f of x, and there are two functions, that is g1 of x, this is g2 of x, and this is the del g1, this is perpendicular to this function is the del g2, and we can take a direction s. So when we are taking some point and we want to proceed in one feasible direction s, so then in that case, what we will write, S transpose into delta F should be equal to lambda 1 S transpose into del G1 and lambda 2 into S transpose into del G2. Now, if S is a feasible direction, in that case, what will happen? S transpose in del G1 will be less than 0 because the S transpose, and that is S and the perpendicular direction to the perpendicular direction to the constant curve will be in the opposite directions. In that case, so this will be less than 0, and the second term S transpose del G2 will also be equal to less than 0. So that is the angle between them is greater than 90 degree. So if these are less than 0, in that case S is a feasible direction, and so if this is a feasible direction, then we can say if lambda 1 and lambda 2 are greater than 0, that is lambda 1 lambda 2 greater than 0, in that case the term S transpose delta F is positive. So in now what happens, like if S transpose delta S is positive, in that case that S is a direction of increasing function value. If the function value is, if the differentiation, the first derivative of the function is increasing, then S transpose in that direction, the value of the function is also increasing. So thus we can conclude that if lambda 1 and lambda 2 are greater than 0, we will not get any better solution than the current solution. In that direction we won't get any better solution. So whatever solution we are there, we are obtaining, that is the best solution, and if we proceed further in that direction we won't get any better solution. So how we will write this condition? So the necessary conditions we satisfied at the constraint minimum points x star are, first is the, that is the constant that we have already seen, that is del f by del xi, j plus sigma of del j belongs to j1, that is for the active constants, lambda j into del gj by del xi equal to 0, and the second condition is for the active constants lambda j is greater than 0, that is lambda 1 lambda 2 is equal to 0, means for if there are j number of constants, then we can say lambda j is greater than equal to 0. So these conditions are called the Kern-Tucker conditions, the necessary conditions to be satisfied for a relative minimum of f of x. Now these are not sufficient conditions, but if we have a convex function, then these Kern-Tucker conditions also become the necessary and the sufficient conditions. That is, for a convex function, the local minima is also the global minima. So this is when we know the active constants. Now, if the active constants among all the constants are not known, in that case, the Kern-Tucker condition, first equation will be same. That is, and second, the Kern-Tucker conditions are modified as, one thing is lambda j is greater than or equal to 0. That is already fixed. Then we will have to add the two other conditions. That is gj of x less than or equal to 0, and lambda j and gj is equal to 0. So you have to add these two conditions, and this total whole all the four equations together form the Kern-Tucker condition. Okay, so this is about inequality constant. There might be some problems where we have this minimization f of x is there, and this is subject to two constants. One is the inequality constant, and the second is the equality constant. That is h q of x equal to 0. So in that case, we can write the Cantaker conditions as the Lagrange function will be, that is we have to add the term related to the equality constant. The first two terms are same, that comes from the previous equation. The third term is related to the equality constant, and the conditions, that is the constant conditions are lambda j of n into g of j equal to 0. This is the first condition. The second is gj less than equal to 0, lambda j greater than equal to 0, and lastly hk is equals to 0, that we have already seen. So these are the Tucker conditions for when we have both inequality and equality constant. So this is a theory relating to this inequality constant optimization inequality constant. We will see through the problems after we just discuss this penalty method. So I'll just brush up the concept of penalty method. So in penalty method, what we do, we uh, penalize the constraints, and then we add it to the optimization function to make it a unconstrained optimization problem. So this is a transformation type of method. What transformation do we do? We transform the constraint optimization problem to an unconstrained problem. So there are two ways where how we can do this penalty method. One is the exterior penalty method, and the second is the interior penalty method. In the exterior penalty method, what we do, we penalize the constraint in the region where it is not feasible. It is in the infeasible region we apply the constraint. And for the interior penalty method, what we do, we penalize the function in the region where it is feasible. We penalize in the feasible region. So these are the two types of constraints. So and then we can write the total function, that is the composite function, as small f of x plus phi of g of x into h of x. So this term phi of g of x into h of x is called the penalty term. This comes from the constraint. So we can have different types of penalty parameters. So if not like phi may be r into h of x, or phi may be r into log of h of x, phi may be inverse function as r into 1 by g of x, or r is into bracket function of g of x. So we can have all these four functions, and these are all transformation functions. Now based on the value of r, we can proceed the solution, and at a for a for a particular value of r, we'll get the optimal solution. So by changing the r value, we'll avoid the infeasible region, and we'll get the optimal solution for the problem based on the given constraints. So this is a sample problem. This is one of the exterior penalty method. What we do, this is suppose the function to optimize is x cube minus 10x plus 2x square minus 10. So this is subject to where x minus 3 is greater than or equal to 0. That is, it is feasible only in this region. So we have to neglect the solutions that come in this region. So how do we do? So we'll write the composite function as x cube minus 10x plus whatever, that f of x plus r into bracket function of x minus 3 whole square. So when we write the bracket function here will be what? Minimum of x minus 3 and 0. So why do we write that? Because see, x minus 3 is greater than or equal to 0. Now if we take a point here, what will happen? So in that case, suppose it is 2.5 suppose. So if we take 2.5, this value will how much? X minus 3 is equal to minus 0.5 and 0. So minimum will be minus 0.5 and it will be squared. So we are squaring the 0.5, that is minus 0.5 square, and we multiply with r. So for a very large value of r, we will be neglecting this solution. So as we move away and away, as you move suppose 1 or like 0.5, in that case this value, this minimum value will be rising. It will be suppose minus 2.5 or minus 3.5, whatever. So as this value will rise, the square value will also be rising. So the function value will be increasing, and in that case we won't get the optimal solution there, so we'll be neglecting that area of the solution. So this is how we apply this penalty function to one, that is exterior penalty method, to a optimization problem. Now the second way is to do an interior penalty method. What it is, similar condition, same problem. That is, we have to minimize this function and subject to x minus t greater than or equal to 0. What in this case, what we do, we'll add the penalty function as r into 1 by g of x. So it will be r into 1 by x minus 3. So in that case, what will happen? So if x is very near to 3, that this value will be very small. Okay, if this value will be very small, and in that case 1 by x minus 3 is large, and so we can, and for a small value of r, we can get a solution where the value will be obtained around the value of 3. Okay, now in this, for interior value problems, so the r value will be starting from 1 and will go near to 0. So when r is very small, that is approximately near to 0, then in that case we will get the optimal solution. But for this, for the exterior problem, r will be suppose starting from 1 or 10, whatever, it will go to 1000 or 10,000 to a very large value. Only for a very large value of r we will get the optimal solution. So that is how we obtain the optimal solution by using this penalty method. And here we do the transform a constraint problem into an unconstrained problem. Okay, any doubts till now in the method? Okay, if there are no doubts, we will proceed to solve some problems. Okay, so first we will solve some conceptual problems based on this, based on what I have taught or what sir has taught in this week. So we have to select the first question is select the correct options. So in case of interior penalty method, we penalize the solutions in the feasible region. Yeah, that is true. In case of exterior penalty method, we penalize the solutions in the infeasible region. Yeah, that is also true. In case of exterior penalty method, we penalize the solutions in feasible regions. No, this is false. And in case of interior penalty method, we penalize solutions in infeasible regions. So first and the second option are correct. Okay, I will just look into that. Now, second problem. Consider the optimization problem given below. Minimize f of x subject to g of x less than equal to 0. Now let us see through this problem. So suppose this is f of x, and let us say we have this is g of x. We take a very simple solution. So g of x less than equal to 0. Let us not do that. This is f of x and this is g of x. So g of x less than or equal to 0 means this is the feasible region. Okay, this is feasible. So we have to get the solution somewhere in this. So this is the optimal solution. So for this question, for so how do we use the bracket operator in this case? So what do we do? One thing is, so how do we write the operation? So the bracket operator will be so the total composite function will be f of x plus r into bracket of g of x. This is the like composite function. Now we have to write the bracket operator. So how do we write the bracket operator? Now if g of x is less than or equal to 0, we can simply write as g of x, because if it is here we need not put any constant in this region. Okay, so we can simply write as g of x is equals less than or equal to 0, then you can write the function value as g of x. Now if g of x is greater than equal to greater than 0, in that case if g of x is uh, in this region, we will put what, we will put the constant is equals to 0. Okay,
Can you
so
repeat once?
yeah, okay. So in this yeah, in this method what we saw, we suppose this was a greater than equal to constant, right? In the example that we saw, g of x, that is x minus 3 greater than equal to 0, so we were obtaining solutions in this region. So now what we did, we wrote the this one bracket function as minimum of x minus 3 comma 0. So minimum means what? So if this value x minus 3, if x is greater than 3, if x is greater than 3, in that case the value will be equals to 0 only, because suppose if x is greater than 3, in that case we will get, suppose the minimum value will be 0. So we'll get always 0 when we are having values in this region. And if x is less than 3, we are getting the value as the minimum of this, that is the x minus 3 value. So this was for greater than equal to constraint. Now when we are looking into a less than equals to constraint, yeah, so it should be this thing. I'm sorry, this is, I did a mistake here. So when g of x is less than equal to 0, that is it is in the feasible region, we'll take what? We'll take the value of g of x only. We'll take the value of g of x only. Like similarly, we'll have a, like for this condition, we'll have a condition like maximum of g of x comma 0. In that greater than equal to constraint, we had this function as minimum of x minus 3 is minimum of g of x comma 0. Here we will have maximum of g of x comma 0. Okay. So if this
Okay,
value is
okay.
in, yeah, if this value is in this region, so the maximum value will always be equal to 0, because this value is always less than, suppose suppose this is minus 3 and this is suppose minus 5 or something. So this value will always be less than 0. So we'll always have 0 in this region. So we are not adding any constraint when we are having the values in the feasible region. When it is in the infeasible region, when gx is greater than 0, sorry, this is equal to 0. When gx is greater than 0, in that case we will have what, maximum this value will be, suppose this is 1, we are taking value of 1, so 1 minus or minus 3, so this will be the maximum value. So it will be 4, maximum of 4 comma 0, so maximum value will be 4. And this so will this 4 will be coming here, so this will increase the value of the function, so you won't be getting a minima, so this will be adding to the penalty function. You understood? So we are having a maximum of v of x comma of 0 in this as the function penalty function in this case. So how do we write this maximum function? So one thing is, if gx is greater than 0, we are getting it as gx only. If gx is greater than 0, we are having gx, we are putting the constant function as gx only, and if it is 0 when gx is less than equal to 0. So in this region we are putting the constant value as this 0, and in this region we are putting the whatever the constant value is there. Okay, this is how we apply the penalty function. So in this case the feasible region was here, so we are, for all the values in this region we are putting the constant value as 0, and for the values in this region we are putting the constant value is whatever constant value we are getting. Okay, so I think this is clear now.
Yes, sir.
Okay, okay, let's proceed to the next question. For a nonlinear optimization problem with inequality constraints, the Cantaker conditions are so nonlinear problem of inequality constraints. The Cantaker are the necessary conditions to solve. These are not the sufficient conditions. These are sufficient conditions only if it is a convex optimization problem. That is, we have only one local minima, and that is also the global minima, or the also a global minima. Okay, now let us see to the fourth question. Consider the following two statements. The interior penalty term is initially set at a small value and then increased to larger value at later iterations. No, this is not true. We have a larger initial value, and then we'll proceed to a smaller value in case of interior penalty term. So in the for an exterior penalty term, it is initially set a large value and decreased to a smaller value at later iterations. So this is also false. In this case also, we start at a smaller value, we increase to larger. So both statement 1 and statement 2 are false. Okay. So let's see the next question. So the penalty function method and augmented Lagrangian multiplier method are also called transformation methods. Yeah, this is true. Penalty function method we have already seen. I will just give a brief overview of this augmented Lagrangian multiplier method. We have seen Lagrangian multiplier method, right? So in it is a similar problem. Is to minimize f of x subject to ci of x equal to 0. So we'll write the this composite function as in this augmented Lagrangian method. A minimum of phi of, we have to minimize this function. Phi of x is equal to f of x plus r by 2 into sigma ci of x whole square. That is, we are adding this term similarly as penalty method. This comes from similar to penalty method, and then we add a third term, the sigma of lambda I into ci of x. So after each iteration, we will be updating this lambda I value as lambda I plus 1 equal to lambda I plus r into ci of x. Okay. So this xk is a solution that has been obtained at the kth step. So this augmented Lagrangian method has one advantage, that we need not take the value of r to infinity. For some problems in this in a penalty method, what happens is that that is for exterior this kind of problem, the larger we have to increase r to a very large value. So to get the very accurate solution, we'll have to make r very large. It is like something 1 crore, a lot very large value of r. One suppose 10 to the power 30 or 10 to the power 100, something like that. So, but when you're taking this augmented Lagrangian method, we need not increase the value of r to very high value. We can obtain the optimal solution, or even for a smaller value of r. So this is one advantage. So I am not getting going in the details of this method. This is similar to penalty method. Just we have to add one additional term, that is lambda I into ci of x. So this is also a transformation method similar to penalty method. In penalty function, second of this is true. The second thing is in penalty function method, a large value of penalty parameter can make the Hessian matrix or transform on unconstrained function ill-defined. Yeah, this is true. So the Hessian matrix, or the, if you are taking a single variable, it is the f double dash of x. So this value will be ill-defined, means this value will be very large in case of when we are having this penalty. So if there is a heavy penalty, so this f double dash x or the h of x will be very large, and in that case we will not be getting any optimal solution. So both statement 1 and statement 2 are true. Okay. So these were some conceptual problems. So we will solve some numerical problems now. So consider the following nonlinear optimization problem, that is z maximize z equal to 7x square plus 6x plus 5y square subject to this condition. So we saw that in the standard form we always do a minimization problem. So we'll convert this problem to a minimization problem. So it will be, so these are two conditions. So we will have two lambda 1 and we'll have to add two constraints. So we'll write these constraints. X plus 2y minus 10 plus lambda 1 into y1 is equals to 0, and g2 of x comma y is equals to minus 3y minus 9 plus lambda 2 of y2 is equals to 0. And we already have z equals to this. One second, okay. Okay, so sorry, we have to add lambda in the second step. So we are not adding lambda here. So it is y1 squared and y2 squared. So we'll now write the Lagrangian form. It's equals to f of x. F of x is minus 7x squared minus 6x minus 5y squared plus lambda 1 into x plus 2y minus 10 plus y1 squared plus lambda 2 x minus 3y minus 9 plus. Okay, so this is the Lagrangian function that we got. Now we'll try to obtain the Cantaker conditions. So one thing is lambda 1 comma lambda 2 both should be greater than 0. Yeah, I am writing f of x in negative because this is a, in the question it was given a maximization way to maximize this problem. But when we do this, when we have to do always the problem in a standard form, we try to convert this maximization problem to a minimization problem. So in the standard form, you can see the problem is in this format: is minimize of f of x subject to some conditions. So when we want to minimize, so how do we do? If we have this plus thing, if we multiply it by the minus sign to the optimization function, then we will do what? We will be minimizing that function. So if we minimize this function, in that case, the positive, the if we minimize the negative of the function, then we will what? We will automatically do the maximization of the function. We are doing it minus so that we are converting the problem to the standard form. Understood? So whatever, whenever there is a maximization problem, always go with the standard form. Else you can like land in some problem sometimes. You might have some confusion. So always go to the standard form and then write it in this form. Because we always do this problem for considering a convex problem. This convex problem is when you have a local minima or a global minima, and we'll have a minima only when we are having a minimization problem. Okay. So lambda 1, lambda 2 greater than 0. Also x comma y greater than equal to 0. These are also the conditions. So we'll obtain the first condition, that is del L by del x is equals to 0. So this will give what? Minus 14x minus 6 plus lambda 1 plus lambda 2 is equals to 0. Second, from the contact, second thing is del L by del y is equals to 0. From this we will obtain what? Minus 10y minus 10y plus 2 lambda minus of 3 2 lambda 1 minus of 3 lambda 2 is equals to 0. Now third condition is del L gj of is equals to 0, that is del L by del lambda 1 to 0. So what we'll have? We'll have only the third condition. Now the fourth condition will be taking the differentiation with respect to lambda 2. So we'll have only this term, x minus 3y minus 9 plus y2 square is equal to 0. This is the fourth term. Then the fifth term will be coming as del L by del y1 is equals to 0. So this implies 2 lambda 1 y1 is equals to 0. And the sixth condition is del L by del y2 is equal to 0. So this is one thing. So how do we proceed now? So one condition is, let us assume lambda 1 is equals to 0. So if lambda 1 is equals to 0, in that case, how do what will obtain? Let us see from the first term. One second, okay. So if suppose you are taking both lambda 1 and lambda 2 equal to 0, so this is one condition. So in that case, what we will obtain, this is greater than equal to 0. So we'll have these two equations, that is from equation 1, if both lambda and lambda, then x will be what? 6 by minus 14, and y is equals to, if both lambda and lambda, y is equals to 0. So this is one condition, x equals to minus of 3 by 7, y is equals to 0. This is one solution when both lambda 1 and lambda 2 is equals to 0. Now we will see if this is the x and y value, then what is the L value, that is we are getting function value. Function value we are getting as minus okay, minus 7 into x squared, that is 3 is 9 by 21, sorry, 9 by 49, 9 by 49 minus of plus 6 into x, 6. So taken minus common, plus 6 into minus of 3 by 7. Equals to 9 by 7. So we are getting fx as 9 by 7 when we are having both lambda 1 lambda 2 equals to 0. Now let us see the second conditions when y1 and y2 equals to 0. Second condition is y1 is equals to 0. In that case, x plus 2y minus 10 is equals to 0. Yeah, it is minus 9 by 7, but we already have a minus in multiplied. So we have minus multiple, since you are writing the this one there is the negative of this function, no? So we are getting this negative value. So we already multiplying it, that taking the minus sign common and then writing the terms, substituting the value of x. Okay, understood? So yeah, this is the f of x. So we are obtaining, but yeah, maximum of f of x will be how much? It will be minus 9 by 7. That is true when we are writing the maximization function. Yeah. So now when y1 is equals to 0 and y2 is equal to, taking both y1 equal to 0, so then in that case we will obtain x minus 3y minus 9. So we have x in terms of lambda 1 plus lambda 2, so we can write x as from equation 1 we can write x in terms of lambda 1 plus lambda 2 minus 6 divided by 14. From here y is equals to 2 lambda 1 minus 3 lambda 2 divided by 10. Oh yeah, sorry. Yeah, x minus 3y minus 9. Sorry, thanks for the correction. So we can write x1 and x and y in terms of lambda and lambda 2. So we'll write in this format: x is equal to lambda 1 plus lambda 2 minus of, I think, minus of 6 divided by 14, and y is equals to lambda 1 minus lambda 2, 2 lambda 1 minus 3 lambda 2 by 10. Okay, we are getting x and y. We will substitute these values in the constraint equations. So it will be what? Lambda 1 plus lambda 2 minus 6 divided by 14 plus 2 into take the so 10 lambda 1 plus 10 lambda 2 minus 60. So 14 by 228, 228 is 56 lambda 1, 28 into 3. So this is one equation that we are getting, and we will get the, from a second equation we will obtain another equation. So how do we write that? Yeah. In the second equation will be x is again lambda 1 plus lambda 2 minus 6 divided by 14 minus of 3 into 2 lambda 1 minus of 3 lambda 2 10 minus of 9 is equals to 0. Again we'll have this denominator as 140. You can take 70 also, I think. Yeah. 5 lambda 1 plus 37 lambda 1 plus 68 lambda 2 minus 660. So these are two equations that we are getting. We have to solve this equation. You can solve using a scientific calculator also. So I will solving using scientific calculator. How values do we get? 24. So after solution, lambda 1 will come as I think around minus 24.1, and lambda 2 will come as minus 3.4. So we can obtain x and y. X will be what? Minus 24.1 minus 3.4 minus 6 by 40. Minus 24.1 minus 3.4 into minus 2.39, and y is equals to what? 2 lambda 1 minus 3 lambda 2. 2 into minus 24.1 minus of 3 into minus 3.4 divided by 10. 2 lambda 1 minus 3 lambda 2. So this is minus 3.8. Minus 2.39 minus 3.8 will get f of x. The maximum value we are taking only 7x squared plus 6x. What is the function? Plus 5y squared. So it will be 7 into minus 2.39 whole square plus 6 into minus 2.39 plus 5 into minus 3.8 whole square. It's coming around 97. So what is the did I do some mistake?
Here condition is lambda 1, lambda 2 should be greater than 0. No, sir. You're getting minus value for lambda 1. Is it okay?
Yeah. Sorry, yeah. These conditions will be not feasible, right? Yeah, we already consider lambda 1 lambda greater than 0. So yeah, this is not a feasible solution.
In LCM, you have to obtain 5 lambda 2.
Where?
5 lambda 1 plus again you have to write down 5 lambda 1 in the LCM part.
I didn't get where what you are saying exactly.
In the last step.
Last step means here,
Like,
second, first condition, second condition.
divided by 70. That is,
Yeah, but this thing is we already, I think we got lambda 1 lambda 2 less than 0, no? So I think this is not a feasible solution already. Okay, so these equations are correct. I think these equations are not wrong. I think.
5 lambda 1 plus again you have to write down 5 lambda 1. That is 5 lambda 2.
Yeah, 5 lambda 1 plus 5 lambda 2. This is fine only, right? So what is the problem in?
Okay, okay.
That is, you are taking the compound, it is 70, right? 14 into 5, so it is 70 is denominator. So 14 into 5 is coming. So 5 lambda plus 5 lambda to minus 5 6 are 30. For 10, it will be 10 into 7. 7 is 21. 21 into 2 is 42 lambda 1 plus 721 into 3 is 63 lambda 2 minus of 630. No, I am saying, did I write any, did I make any mistake in the equations? That's what I am saying. So x plus 2y minus 10, yeah, x plus 3y minus 9. So this is correct. Lambda 1 plus lambda 2 minus 6. So this is also correct. If y1 is 0, then so if this is both are equal to 0, in that case, yeah, I think I did some mistake here. Okay. Answer is given as 702.9. 702. Let us see once graphically what we see. Like, okay, so you will see the conditions graphically what might be something feasible. So one thing is x plus 2y is less than equal to 10. So what will be x plus 2y equal to 10 line? So x by 10. So x by 10. Y by 5. So this is one condition. So one feasible reason is this. So x minus 3y is less than equal to 9 by 9 and y by minus 6 3.
Sir, how you are drawing this, sir? Can you explain once again?
This is from the conditions. This is the first, the constraint is given as what, x plus 2y less than equal to 10. So we are drawing the line where x plus 2y is equals to 10. So what will be the intercepts? X by 10 plus y by 5 is equal to 1, right? So this I'm taking x by 10, that is one intercept here, x coordinate, and the y coordinate corresponding will be what, y by 5. So this will be the 5. So it will get the you'll get the this one x and y coordinate for the line. Like simply putting x equal to 0 in this equation, you will get y
Okay,
equals to
okay,
5, right?
okay.
That's what. Yeah. This is second line is what x minus 3y is less than equals to 9. So here, if I put y equal to 0, we'll get x equals to 9. And if we put x equals to 0 and y is equals to minus 3. So, and it is less than equal to this. So, less than means this area. And the third x and y are greater than equal to 0. So, greater than equal to 0 means x, so y should be here and x also should be here. So, we have only this region. So, one point is what? 10 comma 0, other point is 9 comma 0, and the third point will be the intersection of these two lines. So x minus 3. So what we will get if we just subtract the two equations, minus 5y y is equals to 1 by 5 and x is equals to 8 by 5. So this is 48 by 5. So this similar thing we can do here also. Instead of substituting in these equations, we can similarly solve this. So here if we solve, we will get x is equals to 1 by 5, right? No, sorry, y equals to 1 by 5 and x equals 48 by 5. So x equals to 48 by 5, y is equals to 1 by 5. We solve the constraint equations. Now let us put this x and y values in the this in terms of lambda 1 and lambda 2. So how we'll get lambda 1 lambda 2 from this? So I'll just erase this part and see. Okay. So this is one thing. So y is equals to 1 by 5. So you can put 1 by 5 equals to 2 lambda 1 minus 3 lambda 2 by 10. So this is 2. 2 lambda 1 minus 3 lambda 2 is equals to 2. And if we put here 48 by 5 is equals to by 14. So it will see 5 lambda 1 plus 5 lambda 2, 48 into 14. This is equals to 702, right? 48 into 14 plus 5 into 630, it will be 702. So these are the two equations. Now we will get the solution for lambda 1 and lambda 2 from here. So if we solve, I think we will get we'll get lambda 1 is equal to 84.6, lambda 2 is equals to 55.76. So these are correct. I think I in the previous way I think I did some mistake in the this calculating the solutions of the equation. That's why I got lambda 2 and lambda 2 negative. There was some mistake I did. So this is the easier way to do. So just What I did is similar thing. These are the constant equations. I get the values of x and y from these constant equations, and then substitute this x and y value in that what we obtain the x and y in terms of lambda 1, lambda 2. Now lambda 1, lambda 2 are greater than 0. So this is a feasible solution. Now let us see the value of f of x equal to, I think, 7 into 48 by 5 whole square plus 6 into 48 by 5. I think plus, I think it was, what was the value? 5y square. Whole square. So if we calculate, let us see. 7 into 9.6 whole square plus 6 into 9.6. It is coming around 702.9. We are correct. So this is a thing that I did some mistake in the calculations in the previous method. So this is the simpler method only. So the thing is that whenever you are having some doubt in the calculations, just plot the graph. You will have an idea. Always, like even in the exam, like just if you have some doubt in the solution, just plot a graph. It's easier to view when we have the graph. I plotted the constant lines, and I can see that we can obtain the solutions only at these vertices, because these are the regions where the values can be optimum. So one is 9 comma 0, 10 comma 0, and other is the this point that we obtain, I think 140 by 5 comma 1 by 5. So if we obtain the solutions here like this, then you can get the solution. So have a feel of the solution, always have a graphical feel, and then you can just see, okay, if your solution is correct or not. Okay, I hope you understood this now. It's clear.
Yes, sir. Yes.
Okay. Okay, okay. Using the Kant-Tucker conditions to solve the following problem: maximize xy, x plus y square less than equal to 2, and x greater than equal to 0. So only one condition is given. Choose the correct statement. The feasible region is bounded, so a global maxima must exist. The feasible region is unbounded, so a global maxima may or may not exist. The feasible region is bounded, so a global maxima may or may not exist. The feasible region is unbounded, so a global maxima must exist. Okay, so first let us see graphically how do we what we get. So let us draw the graph. Xy is equals to 0. So maxima is xy. I think this is a hyperbolic graph. We get. I think this is this is a hyperbola, right? Xy. And the thing is that x and y greater than 0. So yeah, so this region is not feasible. So only this region you have to see. X and y greater than 0, and constraint is x plus y square is less than equal to 2. So it will be a parabola only. So y square plus x is less than equal to 2. So if x is equals to 0, y is equals to root 2. And if y is equals to 0, x is equals to 2. So we'll obtain some curve like this, and this is the feasible region, and this is the value of this is the x y. So when we have this, so the feasible region is bounded in this thing, in this curve. So we'll have the global maxima must exist. Now, how do we say global maxima must exist? How do we justify that? Okay, since we already have the conditions, so in that region, yeah, there will be one maxima only. That is the thing how they are justifying this. So a feasible region is bounded, and yeah, we'll have a global maxima in this feasible region only. If the feasible region is unbounded, in that case, we cannot say a global maxima is there or not. Now, a global optimum is at which point? So we have to find a solution. Okay, let's find a solution using Lagrangian. So L is equals to xy plus lambda 1 into minus 2. Okay, so we'll take the derivatives. Del L by del x is equals to y plus lambda 1 is equals to 0. Del L by del y is equals to x plus 2y lambda 1. Del L by del lambda 1. Sorry, this is y1 square. 2y1 lambda 1 equals. Okay, so here also we can have two conditions active, and this lambda 1 is equals to 0, and the second condition is y1 is equals to 0. If lambda 1 is equals to 0, in that case, I think y is equals to 0 and x is equals to 0. So we'll have the maximum value as 0 only. The second case, let us see. Y1 equals to 0, in that case, x plus y square minus 2 is equals to 0. So we can write x and y in terms of lambda 1. So x is equals to, so y is equal to x is equals to 2 lambda 1 square. So it is 2 lambda 1 square minus lambda 1, okay, plus lambda 1 square minus 2 is equals to 0. Lambda 1 square is equals to 2 by 3. Lambda 1 is equals to under root 2 by 3. If lambda 1 is equals to under root 2 by 3, in that case, uh, if lambda 1 is equal to 2 by 3, then y is equals to minus of root 2 by 3, and s is equals to 2 into 2 by 3 is equals to 4 by 3. Now, yeah, this is one thing that is seen. Lambda 1 can take plus minus root 2 by 3. So y1 is minus lambda 1. So when lambda 1 is negative, in that case y is positive. So, but the thing is that one condition is x and y should be greater than 0. This is the initial, this is main condition. And the second thing is lambda 1 should be greater than 0. But the thing is that in this case we are taking 1 second. Okay, 1 second. So in this case, what is the scene? The scene is that yeah, one thing. Okay, the thing is that lambda 1 can take both positive and negative values, but what we found as contact condition is lambda 1 should be greater than 0. So in that case, we won't get a better solution in that direction. But here in this case, what's happening if we take lambda 1 greater than 0, so our like main condition is violated, that is y greater than 0 is violating. So you have to take lambda 1 is equal to minus root 2 by 3, that is a feasible solution. Then only we will get a feasible solution here. And the feasible solution is y is equals to plus root 2 by 3 and x is equals to 4 by that is already there. So in that case lambda is negative, so we can maybe obtain a better solution if we have a better if we have some more information on the constraints. So the answer is it is 4 by 3 and under root 2 by 3. Okay, so this is we have to satisfy the feasible condition. Okay, let's see the next question. Minimize f is equal to minus x1 x2 subject to g1 equals to x1 plus x2 square minus 1 and g2 is equal to minus x1 minus x2 less
Okay,
than equals to.
let it zoom.
Okay, wait. Okay, is it visible now?
Yes, sir.
Or else I will do this. So f is equal to minus f1 x2. You have to minimize this function subject to these constraints it is given. The composite function will be, yeah, we already saw. So these both these constraints are what less than equals to constant, and we have already seen that when you are taking this less than equal to constraint, I think we solved one problem, right? I think this yeah, this one. When you're taking less than equals to constant, so the values, if the value of the constant is less than equal to that value, is less than equal to 0, then we're taking the value of that function is equals to 0. And if it is greater than this constant value, then it is we are taking it as the taking the value as 0. So it is like maximum of g of x comma 0. Why maximum? Like when it is when the function value is in this, when a function value, that is the constant value is here, the maximum value will be 0. So that is, we don't want the any we don't want that constraint to again like to get into the penalty function. But when the value of the constraint is here, so we want, so we take the maximum so that we get the difference of this as the maximum value, and then it will be squared and multiplied by the r to get the penalty function, that is you get a higher penalty. Okay, this is for less than equal to constraint. So similarly we can see it here. So both these constraints are less than equals to constraint, so we will write the composite function as well. At minus of x1 x2 will be there, plus r is there, then maximum of 0 comma x1 plus x2 square minus 1 whole square, plus r into maximum of 0 minus x1 minus x2 whole square. So this is the solution that we get, the first term. Okay, this is for less than, if it is greater than equal to 0, then greater than equal to constant, then we will have a, instead of maximum we will have a minimum here. Okay, now the subsequent part. So comparing the derivative of the composite function dt by dx with Tucker optimality condition that dl by dx, Lagrange multiplier estimates lambda 1 and lambda 2 will be. So let's get dt by dx, what we get. R into maximum of so we have dt by dx on dt by dx too. Okay, yeah, sorry, again I did a mistake here. This 2 will come in front, right? We are taking the derivative of the maximum function with respect to maximum function, and then we are taking plus we are taking the derivative with respect to again the x1, so we'll have 2r, that is maximum derivative of the maximum function with respect to maximum function, so it will 2 will be coming front, and the derivative of that maximum function with respect to x1 will be the maximum of that value only, comma minus x1 minus x2. Okay, similarly dt by dx2 also will get similar, minus x1 plus 2r to maximum of 0 comma plus 2r into maximum 0 comma minus x1 minus x2. So when we write the Lagrangian form, so we have to composite function dt by with Tucker optimality condition, that is dl by dx. So we can write L as what? Minus x1 x2 plus lambda 1 plus y1 square plus lambda 2 into x minus x1 minus x2 plus y2 square. So del L by del x1 minus x2 plus lambda 1 into, suppose this is considered as g, this is also g1, g2, del g1 by del x1 plus lambda 2 into del g2 by del. Okay, fine. Yeah. So we took the derivative with respect to maximum function, then derivative of uh, this variable with respect to x1 will be what? 1. So this is equal similarly as comparable to del g1 by del x1. And here also it will have what? This will be multiplied by chain rule again. We have took the derivative maximum function with respect to this minus x1 minus x2, and if you take the derivative of minus x1 by minus x2 divided with respect to x1, it will again multiplied by minus 1. Similar condition here also, it will be coming 2 here because it is 2x2 square, taking derivative with respect to x2, and here it will be multiplied with minus 1 because it is minus x2. So this how we compare. So a lambda 1 will be what? Lambda 1 will be this part. If you compare these two equations, this part is lambda 1 and this part is lambda 2. The what remains outside is the 1 and minus 1 that comes due to derivative of the this g part, that is x1 plus x2 square minus 1 with respect to x1, and again minus x1 minus x2 with respect to x1. So lambda 1 is equals to 2r into maximum of 0 comma minus 1, and lambda 2 is equals to 2r into minus x. Okay, is this clear, this method? Or if there are any doubts, you can ask me now. So no doubts at all.
Left hand side we are taking del L by del x1, but here putting del x1 and del x2 right side means you have to take with respect to both consigns.
Yeah, sorry. So this is del g2 by del x1 only. Sorry, my bad. Okay, you can compare it to other term also, del L by del x2 also. If you take, you will get you can get the both lambda 1 lambda 2 these values only. This you understood, right? This differentiation you understood. If this is
You
clear,
repeat 1
then
second. You just repeat 1 second, sir.
okay. I will just expand this differentiation. Okay, so what is there? T of x, comma y, what is it? Minus x1, comma x2 plus 2r maximum of 0, comma x1 plus x2 square minus 1 whole square. Sorry, it is not 2r. R plus r into maximum of 0, comma minus x1 minus x2 whole square, right? This is the t function. Now let us take with respect to this is x1 comma x2 del t by del x1. So first term is easy, so it will be minus x2, right? Now the second term we have the function. This is a compound function, so r will be coming out. So this maximum function, if we take with respect to x1, we cannot directly take the difference with respect to x1. So we have to use the chain rule. So what we do? We do del of maximum of 0 comma x1 plus x2 square minus 1 whole square with respect to del of x1 plus x2 square minus 1 into del of x1 plus x2 square minus 1 divided by del x1. Okay, we are using just chain rule here. And similarly the third term will be what? R into del of maximum of 0 comma minus x1 minus x2 whole square divided by del of minus x1 minus x2 into del of minus x1 minus x2. Okay, this is clear. We are using chain rule of differentiation here only.
Okay.
This consider maximum this as a function of f of x, that's f of x whole square. It's like that. So what we will get? We will get minus of x2 plus r into, so this is square, right? So 2 will come outside, so this will, so yeah, 2 will come outside, so other term will be remaining as same, maximum of 0 comma 1 square minus 1, and this term with respect to x1 you will get what? 1 only, and other term for 2r will come out, maximum of 0 comma minus x1 minus x2 into del of, this will be minus 1. So these terms are what? These are equal to similar del g by del x1, del g1 by del x1, and this is del g2 by del x2. So these two terms, this is lambda 2, this is corresponding to lambda 1. This is how we are comparing. Okay?
Okay, sir.
Okay. Okay, any other doubts? So have you done the assignment for this week, or you haven't done?
Still doing, sir. In the assignment number 5, sir, there is one problem number 4. I am not getting the answer, sir. Can you throw some light on that?
Okay, wait. I have to open the assignment. 1 second. Okay. Okay, I'll just check once. Let me open the assignment.
Yes, sir.
Okay, so week 5, right? Question number, which question?
4, sir. 4.
Question number 4. Okay. Solve the following nonlinear program using Tucker conditions. That is 2x minus x square plus y. This question only, right?
Yes, sir. Yes.
X plus 2y less than equal to 10. X minus 3y less than equal to 10. Okay, this is the question similar to the question that we did today, right?
But the
Yeah.
problem is that y function I am not getting. They are not giving any coefficient y square like this. So when I am differentiating that, I am not getting y terms, sir. For differentiating, it's simply given as y.
My term you are not getting like I didn't understand like
Sir, can you open the question, sir? Once.
I opened the question. This is given. Maximize z equals to 2x minus x
Yeah.
square plus y subject to x plus 2y less than equal to 10, x minus 3y less than equal to 10, right? That question only, right?
Yes, sir. Yes, sir.
Yeah. So what is the problem you are facing?
That 2x plus y means, when I am differentiating with respect to y means I am getting one only. So I am not getting equation for calculating y, sir.
So you are net getting equation for calculating. So did you apply the Tucker conditions like this?
No, sir. No, sir. This last class, it was done. I tried, but I couldn't apply.
The thing is that this question actually was misplaced. It should have been in assignment 6. Okay, they have misplaced in assignment 5.
Yes, sir. Yes,
So
sir.
you have to solve this in the method that we did today. Today we
Okay,
solved this
okay,
question,
okay,
right?
sir. Okay, sir. Okay.
Today we solved this using the graph. Also we did by taking this, right, taking
Okay.
the Tucker
I will
conditions and
try, sir. I
solving
will
this
try, sir.
that way only. Yeah, I taught the method now. I think you can solve it for that question.
Yes, sir.
Maybe I don't know the value of this. Okay, I'll just check. He told that the options given are wrong for that question. Okay, let me check. So if we just do the graphical solution, we will have an idea. Okay, what might be the values. So again, x plus 2y is equal to 10. So is equal to, I think this is 10. This is 5. X minus 3y again, so minus 10 by 3 something. This is again 10. So it will be in this region only. So I think only 10 comma 0 is the only solution here, I think. So if we 2 tens are 20 minus, yeah, the options are given wrong in this question. Okay,
Okay, sir.
yeah, so options are given based on the question that is given, that is just solved. 702.9, yeah, that question they have given. To change
Yes,
the
sir.
question, but they didn't change the value. So option, the answer will be, I think, minus 80. So maximum value will
Okay,
be
sir.
at y equals to 0 and x equals to 10. So in that case, you will get, I think, 10, 2 into 10, 20 minus 100 and minus 80 you will get. So yeah, that is, this question is wrong. Okay, I'll give a notice to the prof that to change the options. Okay.
So basically, the intersection point will give the optimum, na, sir, in equation.
Yes, yes,
If there are
yes,
two
yes.
constraints, only the intersection point should be given considered as x and y.
Yes, exactly. Yeah. Very
Okay.
simple graphical solution. Whenever you have doubt, just check with the graph. You
Okay. Okay.
will
Okay,
always
sir.
get clarified. Yeah.
Okay, sir.
Yeah, the options are wrong in this. Okay, so just it's fine. Okay, anything else? Okay, then if there is nothing else, we'll end today's session. Okay, we'll see you in next class. Okay, have a good day.